But not like making it happen, but more saying here's the field or whatever. Now, can you make it happen? That's what I feel.
All right.
All
right, well, good morning, good afternoon, everybody. So today we are going to talk about meshing in ANSYS. So we'll talk about primarily workbench meshing here. So thanks for showing up. Please help yourself with the food. There's a lot of pizza here. And so we'll just get going. Who are we? Ozen Engineering. We are the ANSYS distributor here. We are also a consulting company. We get into a lot of FEA, CFD type of problems. So we are the ANSYS distributor in California, and we provide sales, marketing, training in this class for ANSYS software products. And we also do advanced simulations like these rigid body dynamics, rigid flexible, implicit dynamics, and explicit dynamics. So these are implicit simulations. This is explicit simulation. So we have special classes on those. In addition, we will have, we also have special expertise in fracture mechanics, CFD. Our next lunch and learn will be on fracture mechanics. So we are going to talk about crack initiation, crack propagation, crack modeling, cohesive zone elements, contact elements, and then we call this XRAM method, which is meshless fracture mechanics. There's actually a mesh, but you don't need a special crack tip element, just like you see here. So when it comes to meshing, this is a special topic. So you do meshes for fracture mechanics applications. We will cover this more in depth in our next lunch and learn. So that will be about 2-3 weeks from today. So there's there's really a lot of new stuff in ANSYS when it comes to fracture mechanics. So we'll cover all that new stuff in our next lunch and learn. But today we are going to talk about ANSYS and its meshing methods. So here we are going to talk about processing, and then what is ANSYS meshing, meshing fundamentals, how to launch ANSYS meshing, and we'll talk about ANSYS meshing methods. And there's a special topic. Once you have a mesh, how can you morph the mesh without going through a remesh procedure? You take the existing mesh and you just morph it to look into design variations. We'll talk about that as well. So the pre-processing workflow in ANSYS, as you know, just like any other FEA package, you just start with the geometry. You either import it or create it. Then you do some geometry modifications, some cleaning up maybe, some simplification. And then you send it for meshing. So we are already idealizing the geometry here in the geometry phase. Then when we mesh it, as you know, we fill the solid model with a bunch of nodes and elements. And that solid model is filled in with a bunch of nodes and elements. So there's another set of idealization of the geometry. And then, of course, once we are done here, either FEA or CFD, we send the mesh into the solver, either CFX or Fluent or ANSYS. It may be rigid body dynamics, or it may be implicit dynamics. So what's in ANSYS meshing? It's a meshing platform. It combines and builds on strengths of pre-processing from ANSYS. It combines the strengths from ISM CFD, from T-Grid. Anybody have used ISM CFD tools, for example? ISM CFD was the very first company that ANSYS bought back. Oh, we don't have, or do we? Let me see here. Back many years ago. So let's see. So ANSYS stock is up to $89 today, and this is actually a good day to buy stocks. Maybe yesterday was better, but as you see here, ANSYS stock is supposed to reach $100, not 100 degrees, $100 by the end of the year. As you know, there was a steep dive in the last couple of days. But back in 1999, this is when ANSYS bought this company called ISM CFT. ISM CFT was an independent company in Berkeley and also in Michigan, I believe. They specialize in meshes, especially for CFT applications. So then, you know, ANSYS, the new management at ANSYS, they took a look at the technology, and they said the first thing we need is really a good mesher. And they bought that company, added it to ANSYS portfolio, and then in 2003 they bought CFX. Then you started seeing a climb in the ANSYS stock, and it's still going up. But the point I'm trying to make is ANSYS ISM CFT was the very first company that ANSYS acquired. So what's new in 2015, which is right now we are in version 16 of ANSYS. In version 16, do we have the AC on here? Back to 80 degrees. So let's see. What's new in version 16 is that it used to be that you used to buy separate products. You used to buy ISM CFT separately. You used to buy CFX Mesh separately, Gambit separately, T-Grid separately. The good news is today you don't have to be that confused. You just buy ANSYS Meshing. That's the good news. It includes all the good stuff from all ISM CFT, CFX Mesh, Gambit, T-Grid. So that's the good news, and that's something brand new that, with January of 2015, which is the beginning of this year. So you don't have to get confused about, well, which product is really good for me. You just buy one product. It's called ANSYS Meshing, and it's then you can make use of it. Then you can make use of ISM CFT features, T-Grid, CFX Mesh. All the stuff is in there now. For those of you who likes to use ISM CFT, that's also available. You can still launch ISM CFT just by itself, because we do have some legacy customers who want to just use ISM CFT as a meshing platform. That's also available. But almost all of the features of ISM CFT are available through ANSYS Meshing. So the ANSYS Meshing, in ANSYS Meshing, you can build meshes for CFT, for mechanical, for electromagnetic, and it integrates nicely with other Workbench systems. So, and as you know, the purpose of the mesh is that no matter what you're doing, FEA or CFT, the equations are solved. You're solving the equations basically at the cell nodal locations. So, you know, so like I point out this, it used to be there was a difference between CFT groups and FEA groups. CFT engineers always called the mesh cells and grid points, and then FEA engineers would call them mesh and also element and nodes. So, but now everything, all that terminology is being combined. So we see cell and element is the same thing, node and grid point is the same thing. So now people are using just one platform to do a mesh for both CFT and as well as FEA. So it's important that these days we should be able to do we should be able to create meshes in a fast manner, and also efficiency and accuracy has to be there, and also the quality of the mesh has to be there. So we will talk about all these here in the next few slides. And I'm really happy that, with the new ANSYS versions coming up, the meshing technology is getting faster and faster. Who here is using version 16? Okay. The rest are still on version 15? Okay. You too? You're still on version?
At one place I upgraded, at the other place I didn't yet.
Okay. So one thing you will see definitely is if you move from version 15 to version 16, you will see about 10% improvement in how fast the meshes are done. So it meshes about 10% faster in version 16 compared to version 15. That's one thing you will notice immediately. And as you know, in 2015, ANSYS came up with 3 versions, 16.0, 16.1, and 16.2. So this is kind of, I think it's kind of unprecedented in the history of ANSYS. ANSYS usually doesn't come up with this many releases in a year, but they did it this year. When it comes to meshing, there's not much of a difference between version 16.1 or 16.2. Most of the differences are in a brand new product called AIM, A-I-M, AIM. So there's a brand new product. So what we are going to talk about here is this is ANSYS Meshing in Workbench. This is what we're going to talk about. And as you know, the procedure is really when you go into ANSYS Meshing, you specify global mesh settings, then you can specify local mesh settings, and then you generate the mesh, and then check the mesh quality. After the mesh is done, you may want to check for mesh quality, and ANSYS enables itself to do all that within the mesh module. And there are 2 ways you can launch ANSYS in Workbench. Everybody here a Workbench user? Okay. So you can you can do it from analysis systems, which means if you're doing CFD or FEA, as you know, it starts with geometry and then mesh module. Or you can do it from scratch. You can say under component systems, I just want to go to mesh. If you double click on the mesh icon here, it will launch. It will say, well, first you need to give me a geometry, and then let's go ahead and mesh this. So those are the 2 different ways. And the graphics user interface looks like this. This is very similar to ANSYS mechanical application. You have the toolbars at the top, the outline, the graphics window, and the mesh matrix at the bottom. So the question is, before you go into meshing, how can you configure your geometry? There are a couple ways you can configure your geometry. One is called multiple parts. If you have an assembly, you can have multiple parts in the assembly. That means these guys are not talking to each other. They do not share common faces. So what's going to happen is, for example, you have 2 cubes here. At the interface between the 2 cubes, there is no common interface, so this guy is an independent face, and the smaller cube has an independent face. So what happens in that case is that if you're doing an FEA problem, that's a contact region. ANSYS will automatically create a contact. But if you want to go to CFX or Fluent, then in Fluent, you will have to specify a grid interface, or if you're using CFX, you'll have to specify a general grid interface, GGI, in CFX. So this is what happens if the geometry does not share a common face between them. And then in Design Modeler, you can do this if you have multi-body parts, meaning that you have one cube here, another cube here, and then in Design Modeler, you can form a multi-body part. That means these guys are going to share a common face between them. So if that's the case, you mesh it, and then you don't need contact elements, and it's going to be one continuous mesh. And if you're doing FEA, again, you can specify a different material property here, different material property there. If it's CFX or Fluent, again, it will be a continuous mesh, and at the interface, you're going to have nodes right at that interface that will definitely define the connection point between the two cubes. So, and then you have the third option, which is the multiple body parts. What's multiple body parts? You may have two multi-body parts, and if that's the case, faces will be imprinted on each other, like, and there will be an imprinted face right at that interface. So again, this will again take you back to grid interface in Fluent or GGI, general grid interface in CFX. So those are the three ways. And meshing in 3D geometry, again, the element types that are available are TETs, prisms, pyramids, and hexes. And if you're using tetrahedral meshing method, then it will use TET elements. If you use sweep meshing method, it will use prisms. If you pick multi-zone method, it will be mainly hexes. Hex dominant is not recommended for CFD, especially for CFX. Why? Because CFX doesn't like those pyramid elements, and with hex dominant method, you can get pyramid elements in your mesh. There's also the automatic method. So under meshing methods, we'll cover, we're going to take a look at TET meshing, hex meshing. Well, we won't talk much about 2D meshing. These days, nobody really does 2D meshing. Anybody here doing 2D meshing? It's like a dying art, right? Yeah, many years ago when I went to school, 2D meshing was it. You didn't do 3D meshing back then. But anyway, so, geometry modification, and then, you have to specify a meshing method. We need to think about, are we going to mesh the geometry with TETs or hexes or a combination? So when it comes to TETs, especially for FEA models, tetrahedral meshing has two options. First one is called patch conforming. The other one is called patch independent. What's the difference between them? The difference between them is that patch conforming has to obey and has to honor all the details in the geometry. As you see here, in this geometry, there are sharp corners, there are edges. So it pays attention to all of them, and you get a mesh. You get a nodal point at every single geometric entity. Whereas patch-independent meshing, as you see on this geometry here, it kind of puts nodes and elements on the surface. It doesn't honor every single line. It doesn't honor every single vertex in the model. It just puts a mesh in there. So that's for fast meshes. Patch independent is really a good method. You just go and it will put a mesh in there. It doesn't have to honor all the edges or the vertices, and you'll get and also it will give you kind of a uniform mesh. Whereas as you see here, patch conforming, it has to honor all the vertices and edges, so you're going to get a non-uniform mesh in that case. So that's patch conforming and patch independent. And as you see here, patch conforming, all the details, all the geometry will be captured. Patch independent details will be kind of ignored. There are other options there for the tetrahedron meshing, the Delanoy mesh, which is the smooth growth rate. As you see inside the structure, there's a nice smooth growth rate. And then there's the octree mesh, which is the approximate growth rate. So on the inside of the model, using the step meshing method, you can get two separate meshes as well, depending on which one you would pick. The default, I believe, is the Delanoy mesh, and you will be getting a mesh that looks like that. But if you'd like a more uniform mesh on the inside, you can go with the Oct3 mesh. Then, of course, hex meshing. Hex meshing will end up in reduced element count. And if you're doing a CFD problems, elements align in the direction of flow, you may want to use hex meshing there. So hex meshing will require extra time. You need to clean the geometry, and you may have to decompose, meaning that you need to slice the geometry such that when you mesh it, it will automatically give you a nice hex mesh. So it will require some pre-processing time. And if your geometry lends itself to sweep meshing, this is the best one of all because it's very easy, but you need to have a geometry that lends itself to that sweep method. So you can use the sweep method, and you're going to get all hexes. So, but in real life, you know, it's very difficult to get sweep meshes. I mean, it's difficult to get as engineers. We are never given a geometry that's nice sweepable, so we always have to work through the thing. So sweep meshing is also, you can use sweep meshing to sweep in a tangential direction as well. And when you sweep it in tangential direction, you will also get a bunch of hexes in the model. And let's see, now if the geometry is not sweepable, then what you have to do, for example, if you have a T shape just like this here, this is unsweepable, but then you'll have to slice the geometry. And when you slice the geometry, in this case, in one direction like this, in another direction like this, then this T geometry will become, the geometry will become sweepable. Then that means you can fill it with all hexes. But again, that will require some initial pre-processing. Now, multi-zone meshing is a methodology that came from ANSYS CFD. ANSYS CFD has this multi-zone meshing method, and in geometries like this, which is not sweepable, you cannot really sweep it, but the multi-zone mesher takes care of this, and you can get a really nice hex mesh in geometries that look like that. So that's the multi-zone meshing method, and it's getting better and better every year. They're adding more and more automatic features in multi-zone mesher. I think looking into the future, this multi-zone mesher may be the default mesher that we want to go to because it's giving us a really nice hex mesh and everything, and things are getting more and more automatic lately. So, and there are a bunch of different options in multi-zone mesher as well. You can get a uniform one, and then there's the pay feature as well. So there's really a lot of features. You may, if you have never ever used multi-zone mesher, I strongly recommend you may want to take a look at this. It's really a nice mesher. And in automatic mesher, if you use the default is automatic mesher, and the automatic mesher looks at the geometry, and if it's sweepable, if the geometry is by default sweepable, it will fill it in with hexes. And if it's not sweepable, it's going to put tetrahedrons in there. That's the automatic method. And then we have selective meshing. What is selective meshing? It's selectively picking bodies and meshing them incrementally. So, you know, this is kind of tedious because you have to go and pick the bodies, and then in an assembly, and you say, all right, mesh this first, then mesh this, mesh that. But why do you want to do this? You want to torture yourself? The answer is no, but the reason is mesh seeding from mesh bodies influences the neighboring bodies. So automated meshing can be used at any time to mesh all the remaining bodies, but when you do selective meshing, only affected body meshes require remeshing. And the other thing is you can record this so that the next time you'll have to remesh it, it will also mesh it in that order. So, and here's the difference. If you mesh this block first and then the other block versus if you mesh this one first, then the other, as you see here, there's a difference between the two meshes. So if it's important for you to get a hex mesh in this, so the order in which you mesh, it becomes important. So if you mesh this first, you will automatically get these hexes. That's because that's a sweepable mesh. So that's why we want to go with this, what we call the selective meshing option. And then you can record it, and recording means the next time you want to remesh these, maybe with a finer mesh size, then it will follow the same procedure, meaning that it will follow the same procedure that you started out with, meshing the cylinder first. So then we have local controls versus global controls. What are the local controls? The local and global controls. The first thing we want to do is we want to do global mesh controls, and then we can do local mesh controls. When we in ANSYS Meshing, in Workbench Meshing, when we click on mesh, the details in the lower left-hand corner, everything you see there is what we call global mesh controls. These are all global mesh controls when you click on mesh in the mesher module. And what can you play with in there? You can play with physics preference, meaning that you can actually specify if you're going to do CFD or FEA, and then you can also specify global controls like global element sizes. So you can actually control globally what the mesh setting should be. So the first set of things that you would pick is really physics preference. You know, are you doing CFD problem, mechanical FEA problem, explicit FEA problem, or electromagnetic? Why? Because there's a difference between meshing methods for CFD or FEA. So you need to tell ANSYS what you're planning on to do with the mesh first. Then, if you pick CFD, then you have to let ANSYS know if you will be using Fluent or CFX or Polyflow after that. So that's also important because there is a difference between Fluent mesher and CFX meshing, and so that's you know, that kind of becomes important. And then this feature here, use advanced size function. I really like this feature because this feature, advanced size function, plays a very important role if you have curvatures in your model. Like if you're doing a CFD problem, a shower head problem with a bunch of tiny features, then you should come here and you really turn on this advanced size function option to curvature. And if these small holes are very close to each other or they're very close to the edge, then you may want to turn on curvature and proximity. Then ANSYS will start adjusting the mesh for these tiny small holes, and it's going to fill them in. It's going to pay a lot of attention to these small features, and then it will also pay attention to the case if these small holes are very close to the edge, and it will put a lot of elements in those locations as well. So that's called advanced size function, or in short, ASF. It's really a very good feature in the ANSYS meshing, especially for CFD problems. And here you can see an example. With ASF off, advanced size function off, this is the type of mesh you'll get. With ASF turned on for curvature, as you see this small hole, it's going to pay a lot of attention to that. And then with ASF set to proximity, then it will start filling in this region here, since that small feature is very close to the edges. And also the second region it will pay attention to is there. There's a small feature in the proximity of other features. But if you there's another option here where you can turn on curvature and proximity simultaneously. Then you will get a mesh like this with filling in over there and also filling in the top. So that's also available. So for CFD problems, I would highly recommend using this advanced size function. And then once you mesh it, you want to look at, you want to do some statistics, meaning that you want to look at how good the mesh is, orthogonal quality, skewness, parallel deviation, warping factor, because the mesh that the ANSYS generates, you can actually see which elements are, if you have bad elements, where are those bad elements? Are they close to regions of interest? Then local mesh controls. What are the local mesh controls? After you set the global mesh controls, anything that you do, with respect to, I don't know why it does this on this computer every once in a while, but everything that you do after the global mesh controls, you can actually you can specify local mesh controls after that. Okay. All right. Fast forward to local mesh controls. It's a quick review of what you have done in the past 20 minutes. So, local mesh controls. So after you specify the global mesh controls, you can go in and locally, you can specify sizing locally, contact sizing, refinement locally, matte face meshing locally, match control, pinch, and inflation. All of these are called local mesh controls. And how do you do that? Whenever you insert, you do a right mouse click on the mesh and insert, all of these will appear. So whatever you see on this list, these are all called local mesh controls. These are called local mesh controls. And you can specify sizing on the edges. You can specify a sphere of influence. That sphere of influence will appear as a sphere, and you can put it anywhere in the model. And within that sphere of influence, you're going to get a lot of nodes and elements. And if you're doing FEA, you can do this matte face meshing that will automatically give you a bunch of nodes and elements on the inside of the tube. And you can also do match control. If you have a problem where you're doing like periodic boundary conditions, you will have to match the face mesh. So this is called match control. In inflation layers, if you're doing a CFD problem and you want to specify inflation layers, which are really boundary layers right next to the walls, that's a local control as well that you can specify on selected surfaces. Okay, so then when you're done with meshing, you just check the mesh quality. Why is it important to check the mesh quality? Because as you see here, if you're doing a CFD problem, if you have bad mesh, your residuals will never converge. And if you see that type of activity, it's highly likely that you have a bad mesh, or you have a few cells, a few elements in your mesh that may cause that convergence problem. So you can check things like orthogonal quality, and you can also check boundary layers. So the bad quality mesh can cause convergence difficulty or diffuse the solution. So we need to really check on the quality of this mesh. And here's another example. This is an FEA example. Example showing difference between a mesh with cells failing. So if you're doing an FEA problem, every once in a while you may see a local hotspot, just like in this example here, and you scratch your head, you say, where's that coming from? And it's really, I don't know if you can see, but there's really very sliver type of elements, and those elements is what's causing the bad mesh, the bad result. But if you remesh it with nice set of elements, then you're going to get a nice smooth either stress or displacement solution. So what can you check? You can check a lot of things. You can check element quality, aspect ratio, check warping. Now the question is, should you check every single thing? There are about 8 different criteria here. Should you check every one? The answer is no. There are a couple of things you may check very quickly. Aspect ratio is one that I check very often. Aspect ratio does affect the results. And what is aspect ratio? Aspect ratio is really, in a normal tetrahedral element that may look like this, it's the height of the element divided by the width of the element. So aspect ratio is height divided by the width of the element. And when an element gets really elongated, like this, the aspect ratio becomes more than 10. And if the aspect ratio becomes more than 10, then in FEA, you're almost guaranteed to get bad results. And in CFD too, if that stretch element is in a field where there's tangential components or normal components of velocity, you're going to get bad results in that location as well. So these are, for example, on orthogonal quality. Orthogonal quality, you want to get elements that are close to 1. But if your elements are close to 0, that means that's a worst case scenario. And then skewness is another thing you can check. So these are, this explains what skewness we are looking for. What's the skewness criteria? If it's close to 0, that means those are good elements. If it's close to 1, that means those are bad elements. So there's a bunch of criteria. Aspect ratio, this is really important for both CFD and FEA. So again, so this what we covered is kind of what we have seen in version 14, 15. But what's new in version 16? ANSYS Meshing. First of all, meshing license includes all the meshing like ISM, CFD, CFX mesher. It includes everything. And then after you mesh in version 16, right after you mesh under the mesh details, you can right away plot the element quality. You can right away plot the element quality, and you're going to get a contour plot like this. In this contour plot, the blue elements, that's the quality. The blue elements are good. The red elements are bad. Or you can see that there's some yellows. I can't see any red here. It says minimum is over here. So, but right away, right after you mesh it, you'll get a plot that looks like this in version 16. So this is good visual feedback, so you can right away tell where you have bad elements. And you can see there's an animation here in ANSYS Workbench. Now you have the ability, if you really, really want to, you can actually pick a node and move it. Why would you want to do this? Because if you have a bad element, you can right away click on that node, move that node, and make it a good element just by moving it. So that's also a feature that existed in ISM CFD, and this feature is now available with version 16. It's now available as well. I mean, this is getting really into a lot of detail, but it's a new feature that's available in ANSYS Meshing. So you can dynamically edit and move the node by just clicking and dragging it. And in ANSYS Meshing, you can actually plot element numbers. Until version 16, you could not see the element numbers in ANSYS Mesher. now you can see the element numbers as well as the node numbers. The node numbers, you were able to see them, but the element numbers you couldn't see, but now you have that option as well. And if you use ANSYS Classic, of course, the element numbers are already there. And you can also display the element numbers. If you don't want to see all the element numbers, you can display the element numbers by a certain increment. You can say, I want to look at element numbers from 5 through, say, 100 with increments of 5. And then we'll say, all right, this is element number 5, 10, 15. Then you will be able to see that. Again, that's a version 16. If you're doing FEA, in FEA, as you know, if you're using shell elements, you can specify a different thickness for the shell elements. And now you can display the display style. In the display style, you can say, show me the shell thickness. And right away, you're going to get a plot that says, this shell is thicker than these guys, which is thicker than this guy. So that's also available. Shell meshing again. The default settings in version 15 versus version 16. You can see that version 16 is giving you a much better looking mesh by default. And then if you're bringing mesh from outside, you can actually, using the mesh connections, there's something called in the mesher, it's new, it's called mesh connections, that will automatically detect, just like contacts, and it's going to adjust the nodes so that you can align these nodes and elements with respect to each other. So the picture up top here, it shows connectivity with disjointed faces. And here, after you say detect these connections, model is going to be properly connected, meaning that the elements on the inside, they will be lined up with these elements and they will be automatically merged. So this is also a feature that existed in ANSYS Classic, but now it's also available in ANSYS Workbench. And node merge operation can also be used to join parts, including mixed topologies, meaning that we can actually include a beam with, and also shells with solid faces. So this doesn't apply to CFD, but and then adaptive remeshing. Adaptive remeshing is really great if you're doing an FEA problem, for example here. An FEA problem, oops. If you have an FEA problem where you're inserting something in tight spaces, let's say elastomer. Now, as you see here, the nodes and elements are being remeshed. This is really a tough FEA problem, but this is through the procedure, which is now available, meshes refined where needed during the solution process. As it is solving, it is remeshing the finite element mesh such that it can proceed. Otherwise, with version 15, this problem doesn't run. It stops. It says, I can't solve this because there's a lot of distortion of elements. But in version 16, those elements are being remeshed so that you can actually go ahead with the solution.
That's an example of a remeshing on a transient problem, right?
This is it's still a quasi-static, but there's multiple load steps, so it's quasi-static but close to transient, yes. Yes.
This would be sort of like the elastomer, like an O-ring.
Yes.
But can't you just run that as a hyperelastic material? And
hyperelastic, yes.
Right.
So this material can be hyperelastic, it can be elastic, plastic. You can specify any type of material down in there.
If it is deforming to the level shown here, then
it's going to be hyperelastic,
right?
Yes.
But you can do that in 14 by just setting the material property like a hyperelastic, like a Moody Brillen
right.
model, and then allow it to do that. It doesn't remesh from what I've seen.
In version 14, it doesn't remesh.
Okay.
So if you were trying to solve this in 14, it will probably stop. It will say the element gets distorted so much, the original mesh gets distorted so much. It says, I can't solve this because the Jacobian ratio, there's something ANSYS checks internally. When the element turns inside out, it says Jacobian ratio has gone negative, and it will probably stop in version 14.
But if you just have smaller elements in that area, then hopefully it can keep track of the elements.
Well, not necessarily. Even with smaller elements, they may push on each other so much that it may still turn negative. But this method is a lot better. It remeshes it, and as you see, it's still a coarse mesh. It's not a really fine mesh, but you still get a solution.
Is it doing the remesh between load steps?
Yes, between load steps.
Right.
It stops itself and then remeshes it and continues on from where it left off. So this is really a nice procedure for FEA. And this procedure did exist in ANSYS Classic, but for the first time in version 16, it's being revealed in Workbench as well. So, and then finally, I'd like to talk about this presentation that we did at the ANSYS conference. This is BGA solder joint reliability sensitivity simulation using what's called RBF morph. So, well, what's the purpose of this presentation? This is again in meshing. Here we have a geometry, we have a PCB, solder balls, substrate, mold compound, a die underfill. And in ANSYS meshing, we can go ahead and mesh this nicely, right? This is, by the way, this is multi-zone mesher. It just kind of sweeps and we get all 100% hex meshing using the multi-zone meshing in ANSYS. And these are boundary conditions. The blue surfaces are symmetry surfaces because we are taking 1/8 of a package. It's symmetric on this face. It's also symmetric on this face. And then you go ahead and you specify a thermal condition. You bring up the temperature from -40 to 85 degrees. And you want to look at the stress distribution in the solder joints. And you get some results that look like this. This is the displacement solution. And these are the stresses in the balls. So what happens is when due to shearing, these balls get sheared and you get a lot of stresses in these balls. So what you do is, in problems like this, you want to reduce the stress. You want to reduce the damage done on these balls so that these VGA connections have longer life. So normally, you would specify the ball radius, the bottom radius, the top radius as a parameter in Design Modeler, or you can also use SolidWorks for this. And then what you would do is you create this geometry parametrically, then you mesh it, then you run the simulation, you go back and change the ball size, redo the geometry, redo the mesh, right? This is a typical procedure. And here what we are saying is, let's forget about this. We are not going to recreate the geometry. We already have a mesh. We already do have a mesh. We will just take the current mesh and we are going to morph that mesh. Meaning that we'll pick the nodes and we'll use the same technology that's being used in CFD. This morph meshing, by the way, RBF morph, or morphing the mesh, it originated in Fluent. In Fluent, they were looking, especially in these, F1 formula cars. This is a true story. In F1 formula cars, they want to know slight adjustment on these parts. It makes a big difference in the pressure distribution. But you don't want to recreate the geometry just for a slight adjustment. You take the current mesh and you modify, you morph the mesh. Well, it started manually, then they made it automatic. So now this is available in ANSYS Meshing. This is called mesh morphing or RBF morph. What does it do? You pick a surface and you say, I want to make that parametric. It automatically takes the current mesh and it adjusts the mesh so that you can extend it. And scaling, you can take the current mesh and just scale it in X and Y directions. So you don't have to remesh it. You can use the current mesh. Same thing, rotation. You take the current mesh and rotate it. And similarly, surface offset. You take the current mesh and just make it larger or make it smaller. And then you want to adjust the side. So as you see, the idea here is, to make these things really take the current mesh, change the bottom radius, the center radius, and the top radius, and don't remesh it. Just use the current mesh and just do a bunch of sensitivity analyses. And you can do this in ANSYS mechanical, and then we start out with the baseline. This is our baseline, and then it turns out after doing like 15 iterations, this is the optimum geometry for these solder joints, meaning that the stress, if I go back, the stress will go down from here to here. Baseline geometry gave us a stress over here, and after 22 iterations, the stress went down, I would say, about 20%. And 20% reduction in stress may equal to 30% improvement in fatigue life. So, but this is very interesting. To be honest, I did not expect to see a geometry like this after these simulations, but that's what it turns out. This is the optimal geometry for this case. Yes?
Sorry, is that a static study?
This is yes, it's a static analysis. You just bring up the temperature uniformly and you heat it up and you look at the deformation.
And what kind of solder? Like eutectic?
Eutectic, right, yeah.
Like melts at 186 degrees Celsius, or I forget what
yeah, reflow temperature, I believe 217 degrees centigrade, something like that.
So did you have to turn on the creep effects for that material?
Not for this case. We just wanted to do this as an example.
Oh, okay.
But in real life, we do, when we do this, we do viscoplastic simulation. Viscoplasticity, we turn on viscoplasticity, and which means we also turn on time effects. Time effects are also turned on because, creep is a function of time and temperature. So this was just a demo case we wanted to do really quickly.
Oh, okay.
But in real life, yeah, I mean, the point I guess you're asking is maybe if we had turned on creep and viscoplasticity, we may get a different shape.
Right.
Yeah. So this is for static. Yeah, that's a good point. This is just for static. This is what we got. And then, yeah, that's what the stress distribution looks like. So I just wanted to show you this as well because this is also an option that you may want to use. Given the ANSYS Meshing technology, you can use RBF morph. If you don't want to remesh the whole thing, then you can use RBF morph just to move the nodes around to look at the the changes. And this also applies in CFD as well as FEA. You can change things around in FEA and CFD. So basically, let me do this over here. Yeah, so that's it. So we're so thanks for your attention. Any questions? I know this is, we basically squeezed in the whole ANSYS Meshing class in 1 hour. This is the ANSYS Meshing class that's squeezed down to 1 hour. I had to take out a lot of workshop problems, a lot of the details, but this kind of covers the whole meshing class in 1 hour. So it may be too intense, but you know. So thanks for coming over here. There's still a lot of pizza. Please help yourself. And
I just have one question. Is there anybody interested in a demo license for these machines? Do you see any application in your company for a demo license?
What is a demo license?
Demo for advanced machine, ANSYS Meshing.
I think we have one.
You have one? Okay. Because the meshing is different than what's available in Fluent. This is a separate module.
Yeah. Well, we work with Workbench. We're using version 16.
But this measure is different than the ANSYS measure. It's a different module than Workbench measure.
yeah, I mean, the ANSYS measure now includes all the ISO CFD, all the advanced features. So,
But is it included in the Workbench?
yeah, that's just all in Workbench. So, yeah, so if you have any questions, we'll be around. You're welcome to stay, ask questions, or discuss. If you have a certain problem you'd like to discuss, we can discuss that as well. But I'll stop the recording here.
Not even.